Welcome to this course, in which we will discuss sustainability and reliability of photovoltaics. Today, we start discussing the concept of carbon footprint in photovoltaic, which is also abbreviated as CF. It's an important environmental indicator. The following topics will be covered in this video lecture: the definition of global warming potential and carbon footprint, how to reach a so-called net zero emission goal, and a rule of thumb that help us to evaluate the carbon footprint of a PV module. As we know, emission of greenhouse gases contribute to warming up the Earth by absorbing energy and slowing down the rate at which the energy escapes the space, leading to the climate crisis that we are currently experiencing. Such greenhouse gases include carbon dioxide, methane, nitrous oxide, tetrafluoromethane, and hydrofluorocarbon gases, and others. Different gases can have different effect on the Earth warming. The concept of global warming potential, GWP, was developed to allow comparisons of global warming impact of different gases. Especially, the global warming potential represents the time integrated warming effect due to an instantaneous release of a unit mass, 1 kilogram, of a given greenhouse gas in the atmosphere, relative to that of CO2. A time horizon of 100 years is normally used. In general, people use the so-called CO2 equivalent to evaluate the environmental impact of a product or service on human activities. Carbon footprint is a measure of the exclusive total amount of CO2 emissions that is directly and indirectly caused by an activity or is accumulated over the life stage of a product. According to the 2015 Paris Climate Change Agreement, to mitigate climate change, we need to limit global warming to well below 2 degrees Celsius, preferably to 1.5 degrees, compared to pre-industrial levels. Aiming at the 1.5 degree target, different energy scenarios have been proposed, among which the so-called net zero emissions by mid-21st century is widely accepted. Here we see a CO2 emission prediction. To this end, a paradigm shift from a fossil fuel-based energy system to a renewable-based system is required. The carbon footprint for fossil fuels-based electricity is around 400 to 800 grams CO2 equivalent per kilowatt hour, while that of PV electricity is only around 30 to 60 grams CO2 equivalent per kilowatt hour. The above carbon footprint values are obtained from a life cycle assessment, which will be discussed in a later video. Here we could make a robust comparison between the two energy scenarios. Basically, the life cycle can be divided into 3 phases: initial phase, operating phase, and final phase. For each energy scenario, we have listed the steps included in each phase, as shown in this slide. Accordingly, for each energy scenario, we provide the carbon footprint contribution of each phase in the total lifetime carbon footprint. We can clearly see that for fossil fuels-based electricity, the carbon footprint mainly lies in the operating phase, while for the PV electricity, the initial phase dominates the carbon footprint contribution in the life cycle. The factor includes material extraction production, PV module manufacturing, transportation, and system installation. For this reason, in many environmental profile-related studies, researchers disregard the final phase or end-of-life stage when defining the system boundaries. Here is a predicted carbon footprint plot for PV systems in the Netherlands. The end-of-life management is excluded. 3 energy systems with different energy mix are compared. Ordinary energy mix mainly based on fossil fuels, and energy mix types with the different and increasing shares of renewables. A higher share of renewables represent an energy mix type with lower carbon footprint. With the improved energy mix and provided that PV technology is the mature industrial crystalline silicon technology, the PV carbon footprint can be further reduced. In addition, if we further include increased PV performance, such as applying a hybrid tandem PV technology, the carbon footprint of the PV system can be further reduced. Furthermore, other PV technologies need to be considered as well. Here, we see the carbon footprint of the so-called greenhouse gas emission factors for different PV technologies from a comparative study. The absolute values can be somehow controversial due to the use of out-of-date data for these PV technologies. However, comparative analysis still makes sense. The graph shows that both monocrystalline and polycrystalline silicon had higher carbon footprint than the thin film cadmium telluride technology and ribbon silicon PV. Ribbon silicon PV is a direct wafer growth technology and is kerf-free, and shows a similar footprint as thin film cadmium telluride. More detail will be discussed in a later video lecture. Here we see an historical development of greenhouse emissions from silicon PV electricity over time. A clear reduction trend can be observed. The analysis of corresponding influencing factor can be quite complex. For simplicity, we may use the so-called rule of thumb. The higher PV system lifetime, PV module efficiency and stability, the less material use, the lower the carbon footprint will be. Besides, the carbon footprint is influenced by factors such as energy demand, energy mix, production method, region, and so on. To recap, in this lecture, we introduced the concepts of global warming potential and carbon footprint, which can be used to evaluate the environmental impact of PV technology via the CO2 equivalent emissions. Aiming at the net zero emission goal by mid-century, the energy transition from fossil fuel-based energy system to renewable-based one is prominent. The carbon footprint is influenced by various factors. For simple judgment, the rule of thumb can be applied. However, we emphasize that apart from carbon footprint, there are other environmental indicators, as well as economic related metrics, that needs to be addressed in the PV technology development. More aspects will be discussed in the following lectures.